Trumpf is an industrial machine tooling company and is one of the largest international producers of machine tools. One of Trumpf's major product lines is their laser cutter machines, which can efficiently process and cut sheet metal at an industrial scale. These laser cutters are often a key step in their customers' manufacturing process, and even a few minutes of downtime for unexpected maintenance can be very costly. Trumpf's goal is to minimize the unscheduled downtime of their laser cutter machines by collecting sensor data and harnessing machine learning to predict if maintenance or repairs will be required within a given time frame. Additionally, by identifying trends and patterns in machine usage, Trumpf can develop guidelines for their customers to minimize the risk of component failure and maximize efficiency.
With our project, we have attempted to provide Trumpf with new methods of predictive modeling that they would be able to incorporate into their own infrastructure. Specifically, we have been searching for appropriate machine learning solutions that they could use to increase the reliability of their machines by predicting when the machine would need maintenance and then proactively sending out a technician before the machine breaks down. We have approached this goal by first researching which algorithms might be applicable to this problem, and then by testing our findings in our local environments that are similar to Trumpf's.
We started by creating a customer object using sample customer data from Trumpf to model a random Trumpf customer. Once we gained the capability to accurately create a customer, we applied various machine learning algorithms to identify if a customer's machine state is heading towards a state of disrepair. We tested algorithms that fit in the classification models. This is a form of supervised machine learning where the computer program learns from the input data, then uses the learned knowledge to classify new observations. This fits our goal because our customer states are either in a working condition or in need of repair, so being able to predict the switch from the state of working condition to a state of repair would solve our problem.
To compare how the models performed, we used a common metric called the Receiver Operating Characteristic Curve, or ROC curve. The ROC curve is created by adjusting the sensitivity of the model and plotting the true positive rate against the false positive rate. An example of a ROC curve can be seen here. An ideal ROC curve would have a point in which the true positive rate is nearly 1, while at the same sensitivity the false positive rate is nearly 0. This would mean that the curve is tightly tucked into the upper left-hand corner of the graph. Here are a few examples of ROC curves that we generated based on some select models. A common way to compare ROC curves is to use the area under the curve, or AUC. The AUC score for these models can be seen in the legend next to their names. While none of these models performed exceptionally well, some do show promise. As the semester comes to an end, we are interested in trying to improve model performance, especially with the MLP classifier, and finalize the documentation of our findings so that Trumpf can begin to utilize machine learning in order to increase their uptime and customer satisfaction.